Hey, welcome! Polynomial equations, those long strings of x's and numbers, they might look intimidating, but they're actually packed with hidden secrets. And today, we're going to learn how to crack the code.
Just think about that for a second. What if I told you that the numbers out in front of the variables, the coefficients, what if they were actually little clues? What if they could reveal the solutions, the roots of the equation, before you even did any of the heavy lifting? Well, that's exactly where we're heading.
So for today, let's think of ourselves as detectives. Every single polynomial is a kind of encrypted message. And our mission, should we choose to accept it, is to use the clues, the coefficients, to find the secret solution, which are the roots. And lucky for us, we have a very special tool to do it. All right, so our main tool for this investigation is something I like to call Vieta's decoder ring. It's a powerful set of mathematical ideas that's basically going to be our master key for everything we do today. Okay, so officially they're called Vieta's formulas. And what they do is, honestly, kind of magical. They create a direct bridge between the numbers you can see in the equation, the coefficients, and the properties of the answers you're looking for, like what the roots add up to or what you get when you multiply them. And this is the guy who figured it all out, Francois Viet. He was a French mathematician back in the 16th century who first discovered this incredible decoder ring. He was the one who saw this beautiful hidden relationship hiding inside every single polynomial. Okay, let's break this down. For a simple quadratic equation, the ones with an x squared, let's say its roots are alpha and beta. Vieta's formulas give us these two amazing shortcuts. As you can see, the sum of those two roots is always just negative b over a. And their product, that's always c over a. It's a direct line from the equation to the answer's properties. No fuss, no complex solving, it's that simple. So, we've got the theory, we have our decoder ring. Now for the fun part. Let's actually put it to the test and solve a little mystery. All right, here's our first case file, and it comes from a Telangana state textbook. We've got a cubic equation. Now, we're told two of the roots are 1 and 1, but the third root, well, that's a mystery. We'll call it alpha. So the question is, can we find that missing root just by using our new tool? Oh, you bet we can. Now, here's the cool thing. Vieta's formulas work for any size polynomial. For a cubic, the sum of all three roots is still just negative b over a. In our equation, a is 1 and b is negative 6. So the sum of our roots has to be negative 6 over 1, which is just 6. That right there, that's our master clue. So if the sum of all three roots is 6, and we already know two of them are 1 and 1, well, the math from here is pretty easy, right? 1 plus alpha has to equal 6. And that means our missing root, alpha, has to be 4. And just like that, we found it. No complex factoring, just a quick, elegant bit of detective work. Pretty cool, right? Okay, now that we're all warmed up, let's dive into a really special type of polynomial. It's called a reciprocal equation, and it has this amazing, almost poetic symmetry, a palindromic pattern that totally gives it away. So what makes it a reciprocal equation? It's this one beautiful rule. If some number, let's call it alpha, is a solution, then its reciprocal, 1 divided by alpha, is also a solution. The roots always show up in these perfect little pairs. And you can spot one of these from a mile away. It's awesome. Check it out. On the left, you've got a standard polynomial. The coefficients are kind of all over the place. But look at the reciprocal equation on the right. See that pattern? The first and last coefficients are the same. They're both 6. The second and second to last are the same, both negative 35. The coefficients literally read the same forwards and backwards, just like a palindrome. Now you might be thinking, great, they look cool, but are they a nightmare to solve? And the answer is, surprisingly, no. Because they have this special structure, they also have a really slick and elegant solution method. So let's walk through the steps to crack this palindromic code. We're going to get our hands dirty with this example from the Satyabama University source. Right away, you should see the symmetry. The coefficients are 1, negative 10, 26, negative 10, and 1. It's a classic palindrome. Cracking this is like a 4-step mission, and it's super clever. First, we divide the entire thing by x squared. Now that seems weird, I know, but trust me, that's the move that unlocks everything. Then we rearrange things and group the terms that have matching coefficients. And then comes the magic trick. We create a new variable y and set it equal to x plus 1 over x.
This one substitution transforms our messy equation into a simple quadratic that we can solve in our sleep. So, this is what it looks like after you do that grouping. You see how that underlying structure just pops right out? You get these perfect symmetrical pairs, like x squared plus 1 over x squared and x plus 1 over x. This is that hidden pattern we've been looking for, and it's what makes our substitution trick possible. So after all that clever maneuvering, our big, scary fourth-degree polynomial, it just boils down to this, a super simple quadratic, y squared minus 10y plus 24 equals 0. Solving that is a piece of cake. We find that y is either 4 or 6. Now, we haven't found x yet, but we've found the keys to the kingdom. All that's left is to solve x plus 1 over x equals 4 and x plus 1 over x equals 6 to get all 4 of our final roots. Okay, so we've cracked a few codes, which is awesome, but let's zoom out for a second. What's the bigger picture here? Why does any of this matter once you walk out of the math classroom? Well, here's the real takeaway. This was never really just about finding x. It's about training our brains to see patterns that are otherwise invisible. Learning to spot the symmetry in an equation is the same skill you use to find the underlying structure in any complex problem, whether it's in computer science or finance or physics. Which really brings us to this idea. At the end of the day, the real beauty here isn't just in getting the right answer. The magic is in recognizing that elegant, hidden pattern that made the solution possible in the first place. And that's what I want to leave you with. These mathematical tools helped us see deep structures hidden inside simple equations. So what other complex problems out there, in science, in technology, in our daily lives, are just hiding a simple, beautiful pattern, waiting for someone, maybe you, to find the right decoder ring to unlock them? Thanks for joining me.